everyone, and welcome to the third tutorial of this video series where we're learning how to use the MatPlotLib library in Python to draw graphs, plot functions, represent data visually. So this video is a continuation of tutorial 2 where we were still busy with learning how to draw functions. In this section we're going to be discussing trigonometric graphs, which get quite complicated quite fast, and for that let me just reset the kernel and import the MatPlotLib NumPy as well as the NumPy library. And I'm going to set the axis grid to true, and then we're going to declare a linear space over which we want to define our trigonometric functions. We're also going to define our trigonometric functions as NumPy sine x and NumPy cos x. Okay, so the first trigonometric graph we're going to draw is just going to be a plain graph within a box grid. And so we're now going to look at how to adjust the parameters for this axis so that they appear more visually appealing. So I've set the axis location through the origin, and I've also added a label for the sine graph. So I have to call the legend method, and I've also set the y limits from -2 to 2. Okay, so nothing here is really new, but the problem lies in the fact that on the x-axis we have only integer multiples of 2. And we would rather want to see the intercepts as well as the local critical points of this graph, and the corresponding x values should be in pi or degrees. So this is where it becomes really difficult because we're going to have to define a couple of operations. So the first operation that we're going to have to define is the union operation, because we're going to be defining sets of intervals. The first interval that we're going to define is the x vals radians 1 and the x values radians 2, which are containing the multiples of pi over 6 and pi over 4. And then we're going to put them together in one interval, which we call the x vals radians real, which is then converted to a list. For degrees, we're going to define the intervals x vals degrees 1, x vals degrees 2, and then we're going to merge those together. Those are just the converted values from radians to degrees, so that if you feel like representing your x-axis in degrees, then you can do so. And so now when we want to plot this graph, we can set the x-ticks to x values radians real and replace that with x values degrees real, and it's going to give us this beautiful output, all our special angles appearing on the x-axis. So that's 30, 45, 60, 90, and all multiples of those values along the x-axis from -360 up to 360. But what if instead I would have wanted to have the values on the x-axis to appear in radians instead of degrees? Then the following approach will work for that. First, I'm going to take the x values radians, and then I'm going to convert that to a list, and I'm going to call that x vals rad string. So I'm just mapping those values in that list to a string, and then I'm going to replace the value pi for each element in that list with /pi between $signs so that it can render as LaTeX. And I also have to replace the star, which represents multiplication. I'm going to replace that with absolutely nothing, an empty string. And then I'm going to call that set x vals rad string clean. Okay, and now I'm basically ready. Okay, so I've replaced the labels in x vals rads real with x vals rads string clean, the values of pi with /pi in $signs, and then we've cleared out all the asterisk symbols and we've replaced them with nothing at all. And so this is the graph that we get. I mean, these are multiples of pi over 6, pi over 4, and pi over 3. Okay, and so this is from -2 pi all the way to 3 pi. Okay, cool. So here's an illustration of a graph containing both sine and cos, using the same multiples of pi over 6, pi over 4, and pi over 3. So I've really not done much more. I've just added another plot and another label in my legend. At this point, when you look at the y-axis, the same sort of similar situation appears where we don't actually have the corresponding output values. For pi over 4, we expect a value of √2/2, but it doesn't appear on our y-axis. So we're going to do something similar. First, we're going to define the minimum and maximum y value, and then we're going to define these three intervals: the y value positions 1, y value positions 2, and y values positions 3, which ranges from the origin 0 all the way to k, which is 2, and that's going to contain values of a half. The second set or list is going to contain square root 2 over 2 multiples, and then the third list is going to contain all the values of square root 3 over 2 multiples. Okay, and so I'm going to render that, and then I'm also going to define this new operation which I'm going to call reflect, so that we can get the corresponding negative values for this list. And so I'm going to call those lists yvals -1, yvals -2, and yvals -3, which just takes as argument these three lists above here inside the reflect operation. And then I'm going to take the union of all of those lists. Alright, I'm going to also define the endpoints for our y-axis. That's from -k all the way to k. And then I'm going to put all of those together in one list. I'm going to call that yvals, y values. And now I'm ready to put them all in a list and define the data type as float. Okay, because if you don't define the data type as float, it's just going to be an object, and that's going to be a problem when you try and manipulate the list using the list operations and stuff like that. So I'm going to map all the y values to string values, and then I'm going to call that y values string. And then I'm going to replace all the appearances of square root inside of that list with /square root, so that we can render it as LaTeX. Okay, then I'm going to replace the left round bracket with a left curly bracket, and I'm also going to replace the right round bracket with a curly right bracket. And then I'm going to append to each of those string items in the list, the beginning of that string I'm going to append a $sign, and to the end of that string I'm also going to append a $sign. Okay, and now we're ready to include our y ticks, and I'm going to replace the yvals rel, which is the positions where our ticks should appear, with the elements in the list yvals string clean. Okay, and so I'm going to get this LaTeX formatted axis 0, 0.5, square root 2 over 2, square root 3 over 2, 1, square root 2, 1.5, and square root 3. Here's another example of a trigonometric function. Let's go ahead and define h and j, which are -2 sine x plus pi over 4, and j of x is cos of 2x minus 1. And I'm going to now go and plot those on my axes. Okay, and so I'm just going to basically copy, paste, and add another plot to that axis. And so it should look like this. Okay, so that's my code for it. It's really simple. My graph looks really nice. I have a amplitude -2 sine x plus pi over 4, and I have cos of 2x minus 1 in the same set of axes, with all the grid lines and all the ticks appearing as in a textbook. Okay, let's look at the trigonometric graphs with discontinuities. That's going to be our tan graphs. Okay, and for that, pretty much the same code is going to work. I'm just going to set the parameters m and n again. Remember, m and n are used to define the linear space, the domain of our graph. And then we're going to define k of x, which is going to be tan. And then we're also going to just take that code that we've defined before, and we're going to draw all of that together. But this time I'm going to draw five tan graphs that have different parameters. Well, the first one is just tan of x. The second one is tan x plus a half. The third, we have tan x plus 1. Then we have tan x minus a half, tan x minus 1. And you can play around with the parameters inside. So let's talk about how to save images. If you want to save an image, basically all you have to do is to include the .savefig method in your cell once you've created a plot. Okay, and so inside of the parentheses you will have to pass the string value for the name of the file that you would like to save it as. In this first example, let's save it as a JPG file, and once I run that and I go inspect my environment, my tutorial directory, I see I have now created a new image, sine x JPG, and it appears the resolution is quite high. And if I zoom in, I can see all those ticks maintain their crisp appearance. You can also save this file as a PNG. And if I save that as a PNG, it will appear on my directory with high definition output. Okay, so you can use this anywhere you want in your documents. I can also save it as SVG, which is then useful to use in creating website contents. Scalable vector graphics are quite important when especially building online content. So you can do quite a lot of this. If I zoom in, you can see how clear all the lines remain, and that's the benefit of using the appropriate tools to draw graphs, right? So you should really be using these techniques. So in this section we're going to look at working with circles using yet an alternative method, and in this case specifically making reliance on polar coordinates, which is a really powerful technique. So we don't have to really think of the circle as consisting of branches. I've just reset the kernel and I've imported the appropriate libraries, and over here I have a piece of code where I have defined the origin of the circle, the midpoint of the circle, as x0 and y0. I've defined the radius of the circle, and I've also included a parameter t using the NumPy method a range, and this is going to be our angles that are separated by 0.01 units. And so it's going to start at 0 radians and go all the way around the circle 2 pi radians apart. And so over here I have my polar coordinate for my x values and my polar coordinates for my y values as in sine t and cos t times by the radius, so that I can get my full list of x and y values. And then I'm going to instantiate a figure as a subplot, and I'm going to set all the spines to the origin or through the origin, and I'm going to plot my graph, and it's going to give me this beautiful figure over here. So that's a much easier way of defining circles using MatPlotLib instead of having to cut them up in branches and so on. And okay, so in the next piece of code I'm really just going to change one little thing. I'm going to actually add another point to my graph, which is going to represent the midpoint, and I'm going to represent that with a marker O. So I'm really just going to plot these extra additional 2 points at the top here, the 2 center points for the circle, and it's going to be in orange, and it looks like that. It looks really nice. So now you can start moving that around by changing the values of x0 and y0, and automatically that will just update the circle's position. From the previous sections I have all the tools available to be able to start building a circle graphing calculator, and so that's what we're going to do here. So the first thing we need to do is we need to import all the appropriate libraries, and an additional one that we're going to need is the regular expressions library, which is going to prompt us to insert correctly formatted text. And so over here I have a calculator that requires us to specify the radius of a circle that we want to define, and also to define the center point of that circle. And so basically this is the piece of code which I'm going to run through quickly because it's not that complicated. Print to the screen, we need to enter a radius value, and then it's going to capture that in a variable, and then we're going to put in a number, and then it's going to try and associate that with a floating value by converting the number that we've provided. And if that doesn't work, it's just going to set the radius to 1, and then it's going to tell us that is wasn't a valid input, and therefore the value has been chosen by default. And then it's also going to print another line for us to enter a coordinate pair in the form x, y between braces, and then it's going to associate that with the variable center. The regular expression library will check that our coordinate consists of a number which may or may not have 2 decimal values, as well as another number which may or may not have 2 decimal values, and they can also be negative. So that's what the question marks really mean, is that those are optional. And then it's going to store that into a list, which we're gonna grab the 2 elements from that list, and then we're going to associate them with x0 and y0 and convert those to floating values. If that coordinate pair provided from the user is not an appropriate format, it's just going to choose 2 default values for the center point, and then the rest is pretty much straightforward and the same as we've done before. It's going to set up the polar coordinates for our circle over here, and it's going to plot an axis. It's going to instantiate the subplot. It's going to set the axis spines to through the origin, and then it's going to plot that additional point, that origin. It's going to give it a title, and that's it. So let's check what it does. I'm going to specify a radius of 4. I'm going to give it a coordinate of 1, -2, and immediately I get this beautiful output. So, you know, I no longer have to go and change the parameters in my cell. I can really just use this calculator over and over again. For example, now I want the radius to be 4 units. I want my center to be at -1 and 0. And once again, I get this beautiful graph, and so that's really nice. I can also make it save this image as before. I can just say plot.save fig, and then provide it with circle.jpg. And once I save that, I first have to enter all these values though. It's going to give me a nice graph, if I go check my directory, let me just open that. It's under my desktop, Jupyter Notebook, tutorial 3. Here I have circle.jpg. If I open that, hey, I get a beautiful circle. Now I can use this in my graphs offline. So for the next example, we have a ratio calculator, and the way this really works is the same as before. The only difference is we have to also define these two parametric curves, which are straight lines that go from the origin of the circle up to the circumference. So you can see here I have P and Q, which is based on this linear space between 0 and 1. And this rad value here is a fixed specified angle which is provided from the user by input. It will use the SymPy library to calculate these trigonometric ratios, sine, cos, and tan of the angle provided. Simplified third form. If I run this as an example, we can provide it with a radius of, say, 3 units and a coordinate for the center at, say, 2 and 3 units. And then we have to specify a angle. If I specify 45 degrees, that's going to be a nice easy one because it'll just give us square root 2 over 2 for sine theta. Cos theta will result to the same value, and tan theta is 1. We all know that's true. Okay, let's run this again and play around with it a bit and specify other values. Radius 2, coordinate -1, -1, and angle of 75. And then we get these values. So here we go. The trigonometric values are simplified for us. Next example, we will be building a distance calculator, and so here I have a piece of code which I'm going to explain. So basically, first what we're going to do is we're going to define two pairs of coordinates. So that's x1 and y1. Let's just change that to, say, -1 and 3 and -3 and 4. And then basically it's going to make that into two lists for x and y. And over here I've defined a function which is the distance formula. That's going to be the square root of the sum of the differences squared. Okay, and then it's going to use that to calculate distance function to get the radius, because we're still going to draw a circle based off of that. It's going to instantiate a figure. It's going to add a subplot. It's going to set the axis spines through the origin, and then it's also going to add the ticks, which we already discussed in the previous tutorials, etc. And then it's going to plot the points independently of each other for the x list and the y list, and it's going to also make it into little circles so that they appear on the graph. Before we create a list for our x ticks and y ticks, we will first use a nested if function to check what the relationship is amongst x1 and x2, so that we can decide whether we want our list to range from 0 up to x1, so that we don't include all the unnecessary grid lines to the left. And if that's the case, we're going to check that if x1 is greater than x2, then we're only going to consider, the ticks to go up to x1, because I mean x2 would be included automatically, and then the reverse of that is just in the else if statement. And then we're also going to check if in case our values of x1 and x2 were negative, we're going to check the same thing, that we want to create all the grid lines all the way to the left up to x1. Automatically x2 would then be included, so the else if statement is just the reverse of that. And so that's basically it. And we're going to do the same thing for the y to generate those x ticks and y ticks. We're going to call that x-ax and y-ax, and we're going to pass that in as parameters for the x ticks to plot the graph to give us this grid lines over here and all the way up. Okay, so that's it. And if I show that, it's just going to draw a little graph for me. Here's the set that it printed, the list of x values. It's going to be -3, -2, -1, and 0. So that's basically all. It's just to ensure that we don't have all the unnecessary values to the right and all the unnecessary values to the bottom of this axis as well. So that's what these conditions are really checking for. It's just to make sure that we plot only the appropriate labels, and you don't want to set your ticks to some unnecessary values to the right wherever the circle may not appear. Alright, so in this case I didn't write the functionality so that it requires an input from the user. I've only made it so simple so that we have to specify the x and y values, but that's really not much of a problem. Let's just change that to, say, -3, +4, and let's change x2 to 6 and 9, and it's going to give us this graph. You see, so it really just takes all those labels into consideration that are necessary, and it also prints us the distance for the radius, in this case 2 square root 37. Okay, but if you'd like your radius value to be printed in floating values, then all you really got to change here is the way that the radius is calculated. You're going to want to use NumPy instead. So over here I'm going to go to SMP, change that to NumPy, and it should still give you the same result as expected, except that it's in floating value 12.16552, etc. But it's the same picture, it's the same list, the same radius, it's the same circumference, it's the same labels, everything is the same except this value is given in decimal form. Okay, cool. So that basically concludes for this section. Up to now we've been only using the NumPy and MatPlotLib library to be drawing graphs. And in some circumstances that may be overkill because NumPy itself also comes with plotting capabilities. And so I'm going to show you some features that we may utilize in order for us to be able to draw nice plots without really requiring the matplot library. Okay, so for that, let me just reset the kernel again. Import the symbols and the plot library. And then for our first plot, I'm just going to declare symbols because this is the standard way when using the NumPy library that we have to declare symbols, which we will be using in our functions. In this case, I'm not really going to use a function. I'm just going to pass in the symbol x and then I'm going to square it. And then I'm going to plot that between -1 and 1. So basically the first argument is the function expression, x squared, and the second expression is the domain, in our case x ranging from -1 to 1. And if you plot that, you're going to get this parabola. So automatically it will label the y-axis for you and the x-axis for you. Okay, here's another example. The problem with this one is that when you call plot show, which is the standard way of showing your graphs, it's going to give us two graphs because it's plotting the graph and it's also showing the graph. So to suppress one of those, we're going to set the attribute show equals to false, and then it's just going to render the graph once we plot .show the graph. Okay, so but there's a lot more we can actually do. We can also change the x labels. In this case I'm going to just call it time. You can change the y labels. In this case I'm going to render some LaTeX expression ax squared plus bx plus c. I'm also going to give it a title, and then we're going to just put a space after the title. I'm going to show that plot. It looks like this. So that's just a standard parabola. You can come up with other functions. You can also set the limits as we did before within the matplotlib library, where we had the x limit and the y limit. In this case from -2 to 2 on the x-axis and from 0 up to 2 on the y-axis. Let's change this to see if it has any effect. Let's suppose you want to put -2, then yes, it's going to go all the way from -2 up to 2. Still the same features and still the same capabilities. It's just that the syntax is a little bit different because you have to put everything within the plot method. Here's another example where we're going to change the size of the graph to a 4x4 figure. Well, let's actually change it to a 6x6. And so this is what you get, quite a big, large figure. Okay, here's another example of 3 functions on the same axis using the NumPy plot library. In this case, I'm just going to pass in 3 function definitions. That's x, which is a straight line, x squared, a parabola, and x cubed, a cubic function. Between the values for x from -1 all the way to 1, I'm going to suppress the plot. And I'm going to set the size of the plot to 5x5. And if I run that, I get this nice graph automatically labeled for me. I didn't change any of the titles or axes. Okay, so here's an example where I've changed the color of the 2 lines, but here's a bit more to discuss here. We're actually going to use the extend method to say that we want to plot another graph on top of that axis. All right, and once again we can still use the RC parameters to set the axis grid. It shouldn't actually have any effect on the fact that we're using the NumPy library. It should still be able to. So let's try that. Still set the axis grids to true using matplotlib library. The NumPy library actually uses the matplotlib library, so if we want, we can turn that on, and then we can just redraw this graph and it automatically should have grid lines. Okay, cool. So that's not really nothing to worry about. Just because you're using NumPy doesn't mean that you can't have the grid lines. So in this section we're going to look at implicit plots in the NumPy library. For that, I'm just going to reset the kernel, import the appropriate NumPy library, and declare the symbols. And then for our first example, we're going to look at the circle using the implicit plot library. And basically here the problem is that the aspect ratio of the axes is not correctly adjusted to give us a proper circular figure. So we're going to have to go and set the aspect ratio to 1,1. using the plot.aspect_ratio method, and that's just going to fix the problem for us. Okay, so that's really not much to worry about. If your graph is a little bit too small, your figure is a bit too small, then of course it's going to cut out some of the lines. You might want to make sure that your figure size is much bigger than your domain, right? So in this case, it's going to cut out everything from less than -5 downwards and so on. So you might want to set that axis figures to something bigger. Okay, so for example, just setting it to 5 by 5 kind of does the trick. Okay, and that's fine. We're happy. The cool thing about the implicit plots is that we can also draw any other implicit equation. So here we have an example of an ellipse where the aspect ratio is still set to 1 by 1, and that means that our grid lines are going to be squares. So here's another example of a circle which has been translated by a certain number of units to the left and up. However, here I don't include the center point. You can go and do that in a very similar way as before by adding that additional plot using the MatPlotLib library. Once again, the power of implicit plots is really cool, because here I have an example of a hyperbola x over 3 squared minus y over 5 squared equals to 1 between -10 and 10, and between -10 and 10 on the y-axis. And I'm going to get this hyperbola. Okay, that's really nice. All the conic sections are easy to draw using the implicit plot library, as opposed to using the MatPlotLib library. In certain circumstances, you might want to use this instead. Okay, so that's what I'm illustrating to you, is that there's many alternative ways of doing one thing within programming and maths. It's pretty much all versatile. You can do many different things in many different ways. Yet another example where I've translated the hyperbola to the right and I've translated it up. Okay, so I get that. We can also do parametric plots. So for this section, let me just add a title, parametric plots. So we're also going to import the parametric underscore plots, plots underscore parametric. And we're also going to import the trigonometric functions, cos and sine. We're going to declare the symbol t. And here's our first example using parametric equations. That's going to be cos t comma sine t between the parametric value -5 to 5. And so when I run that, it's just going to give me this graph. Once again, everything else is pretty much standard, and we've seen that before. We can also set the x scale and the y scale to linear, right? All that's going to do is basically the same as the aspect ratio. It's just going to make sure that it's all equal. This over here is an ellipse. We're giving it an x argument of 3 cos t and a y argument of sine t. But if I set the aspect ratio to 1,1, then we're going to see that much more clearly as rendering as an ellipse, right? So in the next example, I'm just also going to import the NumPy library again, because I might have erased it in the kernel. And the function that I'm declaring here is f, which is r cos t, and r is 2. Here's another one similar to that. Okay, it's the function r cos t times 3 and r sine t times 2. Okay, and it gives us this squiggly shape. It's really nice. So in this section, we're going to look at how we can draw polar graphs. All we really have to do is we have to just specify the projection inside of the axis method to polar. And so let me just reset the kernel and import the appropriate libraries. And so here I'm going to import MatPlotLib as pyplot and NumPy as np. Over here I'm also going to set the RC parameters axis.faceColor to none, because what I would like to also illustrate is this additional feature that we can change the color of the grid to any other color. Okay, but in this case it's just set to none by default, but we're gonna change it to other colors to experiment. So our first example is just an empty axis with no graph, a 6 by 6 figure size, and inside of the axis method I just specify projection equals polar, and it's going to give me a circular axis. So basically that's a polar axis starting at 0 degrees all the way up to 360, and it's also going to give me this range outwards for the radius. And obviously, because I haven't specified any function or anything like that, it's just going to go all the way to 1. So let's just see what the face color does. So if I set this to black and I re-render that, it's just going to give me a black axis, which is nice because I can change the color of any of my graphs and then change the color of the graph itself to anything contrasting to that. So I can make none. So this is the default color, and that's the one that I'm just going to stick to. Over here I have an example where I've specified the radius starting at 0 all the way up to 2. So this is basically a spiral, because as the angle theta varies all the way from 2 pi it's just going to go outward. Okay, it's going to look like this. So that's really nice. That's how we can use polar plots. Here's another polar plot example where I've just changed the position of the origin. So we will set theta 0 location. You can change that to west, north, east or south, whatever. I'm just going to put it all the way west. And then it's going to start here, 0 degrees, 45, 90, all the way around. So that's something really nice to keep in mind when working with polar plots. You might want to change that to north, and it's going to start at the top, 0, 45, 90, and I'm sure you can also specify the clockwise direction. Just going to look that up on the internet, I'm sure you'll find something. So here's another example, which is called a cardioid. It's basically like a heart shape. I've just set this back to east, so it's 0 degrees, 45, and you're going to get this because the function is defined by 2a 1 minus cos theta, where a is 4, depending on the values of theta, ranging all the way from 0 all the way to 2 pi in increments of 0.01. And yeah, you get this cardioid shape. We also have another example here, which is a bit more intricate. Okay, and this is called the rose. It's a rose. The function is cos k theta. So k is going to specify the number of petals that it has. In this case, it's just 3. So, but you can make that more. You can make that to 6. So now you're going to have 6 petals. And if you look at it, it's got 1, 2, 3, 4, 5, 6. That's really nice and everything. I'm sure you can appreciate that. Okay, so yeah, that's it for this section. So we'll see you in the next one.